We do what?
Will we be able to use the calculator on the test?
Yeah, you can't use it after the first test. You can use your calculator anytime you want. So we have times in here where we use calculator quite a bit, and then we don't use it. And so this one you could use it. Let me think about that. You know what? I need to think about that calculator thing. I'll think about that. All right. Well, anyway, I want to set the tone here a little bit. I'm not trying to teach you something that is ridiculous, but you're not going to hear this. You're not going to hear this lesson in your math class. Even though it has to do with numbers and calculations, they're never going to do that. Why would you never hear this lesson in your math class? Yes? They use these theoretical numbers where 5 is the perfect 5. And you don't. You guys use measured 5s. And a measured 5 might not even 5. Right? It might not even be 5, really. So, to make a long story short here, if you look at this, some statisticians got together and said, since you're using measured numbers, what are some rules that we can make up when you start doing calculations that would make it so you're not lying to people? You want to be as truthful as you can. We know all of your measurements have error, but maybe they don't have a little bit of error, and so we don't want to be truthful. So, anyway, yes? Yeah. So let's take a look at the first one here. They figured out, not me, I didn't figure out, they did. It said, if you're going to multiply measured numbers, then you need to round off to the least number of sig figs. You say, why? See, if I'm in math class and they say, what's this times this, you need to put that down in math class, don't you? Because that is the exact answer. Now, it should bother you a little bit to say, well, why am I not writing the exact answer? Because this is a lie. With measured numbers, you're telling me that they calculated the area. This is area, isn't it? Isn't it a square meter? It's not a meter anymore, is it? Isn't it area? You're telling me they calculated the area of something to tenths, hundreds, thousands, 100,000s place. But none of your measured numbers went down that far. How could you tell me something to 100,000s place when your measurements didn't go down that far? You're lying to me, aren't you? So I know it bothers some of you who are really mathematical, that you don't like to put that, but when you know, you say that's exact. We're talking about measured numbers. So what are the rule again? The least number. So how many sig figs here? 3. And how about here? And the least number is 3. Now, watch now. 1, 2, 3. When you want to round to 3 sig figs, do you ever look at the fourth one?
Absolutely.
You have to.
You have to.
Do you ever look at the fifth one? No. I only look at 1, right? So if I want to round to the third sig fig, I look, and you are not big enough. You have to be 5 or bigger, and you're not. So I'm writing 3.33. Here's a division problem. Ready? How many sig figs?
3.
Wait, everybody should say 4.
4.
How about here?
2.
And the least number is?
2.
Okay, so let's go down here. 1, 2. When you round around to 2, do you ever look at the third one?
No. No.
I thought we went over this.
You have to.
You have to.
You have to.
Now, ready? Now, that 6 is big enough, and so that 4 is not going to stay as a 4. It's going to go to 25, right? Are you okay on that? So when you multiply or divide, the rules are the same. You have to round to the least number of sig figs in any of the measurements. But statisticians, not me, they figured out that you can't use the same rule for adding and subtracting. I didn't do it. Sorry. What's the rule for adding and subtracting? What's it say?
Limit and round your answer to the least number of
Okay. Now, even though your math teacher is going to tell you that the decimal places are to the right of the decimal, that's not true. Every number is in a decimal place. All right, we have the decimal number system, isn't it? Its power is a 10. Every number is in the decimal number system. Now, so look at this right here. You don't say sig figs. You said hundreds place, tenths place, ones place. So what's the least number of decimal places? The ones place. Now, watch. when I want to round off, right here. When I want to round this number off to the ones place, the 3 is in the ones place, isn't it? Either that 3 is going to stay as a 3 is going up by 1, right? When you go to round to the ones place, do you ever look at tens place? Ever?
Always.
Always.
You have to.
Let's watch. And this one is not big enough, so I write 53. All right, let's try another one. Here's the one that kind of fooled you a little bit yesterday. Here's one. This is a division problem. So we do sig figs, don't we? All right, how many sig figs are in 150? Be careful.
2.
That's right, only 2. All right.
Is that right?
There's no rule that makes that is a trailing 0, but there's no decimal, is there? So it's only 2 here and only 1 there. Now, if you're going to round to 1 sig fig, either that 3 stays or it goes up to a 4, right? What do you think? Oh, you're going up. You're going up. Now, you don't round 37.5 to 4. You just put a 4 in the tens place, don't you? And so you have to put the 0 there, make sure the 4 doesn't slide back over. So, but I didn't put a decimal, did I? So how many sig figs are in that right there? How many sig figs right there?
1.
I did it. We rounded to that. I'll show you one more thing, and then we'll move on. Somebody way back, it's either middle school or elementary, it's somewhere. Somebody was trying to show you rounding, or maybe you taught yourself, I'm not sure, but here, round this to the nearest whole number. What do you get?
4.
Why are we not all saying the same answer if you all got taught how to round? Round it to the nearest whole number.
5. 4. But it's 4. It's 4.
Okay, so let me get this straight, okay? Let me get this straight. Some of you have been taught this.
Short of 5.
That 9 makes that a 10. That 10 makes that a 10. That makes it a 5. 5 makes a 5. There's no such thing as that. You cannot do that. If you tell me to round to the nearest whole number, will I look at the next number or look at tens place or not?
You have to.
I have to, but I don't look at anywhere else. Now, some of you don't like me telling this because you were sure that this would round to 5. No.
No, they don't.
And I'll give you a clue. If you're on The Price is Right, and they said, is this number closer to the number 4 or to the number 5?
4.
It is. It's slightly closer to 4 than 5, isn't it? And it would round to 4. All right, what do you think about that? Is that pretty easy? Again, just a thing. If you take physics and you do some calculations with sig figs, same thing's going to happen. But all the scientists in the world and all the engineers, they know that that's what happens with measured numbers. All right, let's try another one. Let's flip over to this other page here. I'm gonna wait to do this on Monday. It's a smaller part of the test, but I'm gonna do this part here. I'm gonna practice. I want you to volunteer. Before you volunteer, wait a minute. I want everybody to try number A and C and E and F, and just tell me how would a scientist or an engineer, how would they what would they write down as the measurement with those things? Okay, so let's try it.
Yeah.
Okay. So ready? A, C, E, F. A, C, E, F. Excuse me.
What is the measure?
Oh, these are, I'm sorry. You're right. Good question. What is a unit? The units are centimeters. It's just bigger than normal centimeters because I had to blow it up. All right. Has everybody got A done? B? A, C, I mean C? C?
Please do one.
We'll do A, C, E, and F, and they'll see what everybody gets. All right. Almost there? Almost done? Why don't we, can everybody do a mask check, please? Because we're in the right we're supposed to. So everybody put your mask on. I hate these. I hate them.
Same.
But I don't want to go to all remote, that's for sure.
Yeah, that's not good.
So don't mess around with that. All right, let's everybody, you said you want to volunteer. Which one do you want to do?
I'll do, C.
C? Okay, what would you put?
I said, for C,
Yeah.
13.25.
Okay, now, I'm not telling you if that's right or wrong, but let's take a look at it. I'm gonna look at it real carefully here. C. Now, we know it's 13.2 something, is that right?
Yes.
And then we run out of lines, don't we? So we have to guess in that gap. And so do you think that arrow is halfway across?
I,
No.
okay.
So if it's halfway across that gap, then you would say 5.
Actually, I think it's 4 now.
I'm fine, but I'm just saying, so how many people put 13.24? Okay, how many people put 13.25? Anybody have 13.23? Okay, so I think I'm all right with either one of those. And you did the right number of sig figs. Let's do another one. Zoe, which one do you want to do? You want to do A, E, or F? Okay, go ahead. Okay, 12.50. Let's take a look at A.
4.9.
Now, does she need to put 12.50 or could she have just put 12.5?
Have to put 0.
She has to.
Why?
Because you have to guess 1 in size. Significant.
Okay, so if you didn't put the 0, then I know you're telling me you didn't have a ruler that had 10th place lines, but you did have a ruler with 10th place line. That would be a lie for not putting a 0 here. Get that?
That's not good.
Now, if you thought it was, did anybody put 12.49? Okay, I would take either one of those. Got that? I think you did a good job. Let's do another one. Who wants, any volunteers? Tim. Tim. Which one do you want to do, Tim?
I'll do E.
Okay.
I did 10.29.
All right, I'll take a look. I'm going to take a look at it. E. 10.29. Okay. Anybody else have anything else? What do you have?
10.30.
That's what I had.
I think either one of those would be fine. Again, you can't put 10.3 though. Can't put 10.3. And then look at number F.
Oh.
Yes, Will.
I got 12.00.
11.99.
I think either one of those are good, but notice that 12 has to be, if you use this ruler, you have to have hundreds placed, don't you? All right, I think we got that down, right? We got that down?
A few more
Okay.
for practice.
What now?
So we just do a few more for practice.
Well, since they seem like we got all 4 of them right. Is there another one that looks tricky?
I think I and D. I think.
Let's do I.
Eyes and
Yeah.
Incan.
I don't know. It seems like it's kind of like we've been doing.
Yeah.
No.
Yeah, I think we've done enough of those. Now, what I'm going to do is show you another part of the chapter, and here's some good news for you. The good news for you is the author spent 7.5 pages trying to teach how to convert different temperature scales. Now, the reason he did that, he wants to show example, another example, another example, another example. Probably in about 15 minutes, maybe 20, I would have taught all of that, and I can see you not even reading those 7.5 pages. And also, I don't see why you couldn't go to your homework and say, I can do all those temperature conversions right now. So when we get done with that lesson, you'll have a whole bunch of homework questions you can do. Yeah.
Oh,
All right, well, first of all, temperature is one of those things that we use. We'll be using that in one of our labs. If you live in the United States, I don't know of anywhere else in the world that uses the Fahrenheit scale. Unfortunately, and I hate to tell you this, but nobody else in the world cares about the Fahrenheit scale. They don't care about it. Now, you might think it's unfair, but you should know about the Fahrenheit scale and you should know about the Celsius scale. The rest of the world uses the Celsius scale. All chemistry labs use the Celsius scale. You get that? Physics lab, what? We're going to talk about Kelvin. We'll talk about that. Now, so if you said you like the Fahrenheit scale, then tell me all about it. Who developed that scale?
Fair.
No, not Faraday.
Mr. Fahrenheit.
His name was Fahrenheit, Gabriel Fahrenheit, and his actual name was Fahrenheit. That's kind of weird. There were many thermometer scales, many, throughout history, but Fahrenheit was one of the first people to use a material called mercury. And mercury is a dense liquid, but it's a metal. It's like the only liquid metal at room temperature, okay? So it was so dense that you could make the thermometer maybe only this big, and it could actually measure pretty small changes in temperature. So anyway, so here's the Fahrenheit scale. And so tell me everything you know about the Fahrenheit scale. What's something you know? What do you know?
Freezing is at 32 degrees.
Freezing what?
Temperature
Freezing what?
of water.
Yes, it. So the freezing point of water is 32 degrees Fahrenheit. Tell me something else you know.
Oh,
Yep.
the melting, point of water's boiling is T12.
The boiling or melting?
Melting.
Melting is 32 degrees.
Boiling.
Ah. So anyway, so boiling is 212 degrees Fahrenheit. What's the freezing point? What's the melting point of water? That means if I had ice down here and I heat it, when did it start melting? 32. What's the freezing point? That means you have a liquid and you're cooling it. That's the same thing, isn't it? So the melting point of water and the freezing point of water are the same thing, huh? Yes.
This isn't relevant to this, but I think I left my phone in the bathroom during lunch. Can I go see if it's
Wow.
working?
What were you guys doing?
What were you, just wait.
I'm not saying you shouldn't go to the bathroom. I'm not saying you might not look at your phone, but you better go get it.
Sorry about that.
That's a little suspicious, honestly.
If you want to watch a recording of her asking to go to the bathroom in front of her phone, that's going to be online tonight. So, anyway, what else do you know? Do you know? And I made a misprint here. This is supposed to be a 72, but if you said what's a comfortable room temperature, most people would say somewhere around 72. Okay, 72 is a pretty comfortable room temperature. And then, what is your body temperature?
78. No, 96.8.
98.6. Okay, so now, so let's say that all of you think, well, I think I know 4 things about the Fahrenheit scale: the boiling point of water, the freezing point of water, a comfortable room temperature, and my body temperature. That's about all you know. Do you know what absolute zero is in Fahrenheit? I doubt, without looking.
And melting. We know.
Oh, it's like negative 460.
Oh,
pretty
it's
good.
almost like you love.
That's pretty good.
Oh,
Yeah,
and,
very few people know that. Okay.
the moon.
Well, okay. Now, what now?
The moon.
The moon is cold
Yeah.
On one side.
I saw that in,
It can also be hot on the other side.
wasn't like around 270.
Got it wrong.
Well, it is true. It's over 200. It's it can be over 200 degrees in the sun. It can be minus 220 in the shade.
China's like on the dark side of the moon.
What?
China has people on the dark
Trying to
side.
be your date to hotel.
They have people where?
On the dark, on like the dark side of the moon.
Oh, right now? I haven't read that. You're saying they're there now?
They're there, or they have been there like recently.
Oh, okay. I don't know why we don't make a bigger point of that in our news. I also know. Do you know that China has a thing on Mars? You know, it has a probe on Mars and taking pictures. So we are too. But you don't hear about that anywhere else, do you? By the way, I'm not your astronomy teacher, but I'll tell you a 30-second lesson. What happens is here's the Earth, and here's the Moon. Okay, and so it takes, you know how long it takes the Moon to go around the Earth? It's called a moon or a month. That's where we got the word month. That's about 28 days. So it takes about 28 days to go around here, about 28. Now, how long does it take the Moon to go like this? This is called revolve. This is called rotate.
A day. Oh, every second.
No, that would be a fast moon, boy. At night, when you watch the moon, you would be blurry, wouldn't it? So, how long does it take the moon to do this?
24 hours.
It takes the Earth 24 hours. You know how long it takes the moon to do that?
Millions a year.
About 28 days. So I want you to think about that. Ready? So here, this part's facing the Earth, and when it goes over here, when it goes 1/4 of its revolution, it's also rotated 1/4. That's why we always see the same side of the moon. So the dark side of the moon is not really a dark side, because when we don't see the moon, called a new moon, guess what part of the moon is lit?
It's getting beamed.
The other side that we never see. So the dark side of the moon, even though it's a Pink Floyd album, the dark side of the moon is actually simply the side of the moon that never faces the Earth. So it can be lit. It can be lit. But until about 1960s, no human had ever seen that side of the moon. And they sent some people around, or they sent a spaceship around, a probe around there, and they took pictures. And so even though you say they're on the dark side of the moon, I have no idea right now. I don't know what the moon phase is, but it could be light or dark there. Yes.
What if other aliens on Mars, or like they could
Well,
be holding up a picture, like what about this?
Right now, we have a probe there, and China has one, and we're taking some pictures, and some of the probes are actually moving, and they're moving from one part of Mars to another, and they're taking samples,
Did you find
and right now they haven't found anything quite unusual at this point. So I think they found something really unusual. It's possible they would not tell you until they had time to figure some things out. People don't like the idea that you discover something living on Mars. I don't think we're not quite ready for that yet, if there is such a thing. So it's possible the government would try to hide that from you for a while until they could figure out more about it, and how do you tell people without getting them panicky, that kind of thing there.
What do you think they have?
What now?
Do you think that there's like aliens that are in?
No, I don't. At this point, I have not seen evidence of anything on the moon or the Mars.
I heard there.
I know that there are things that are unidentified, UFO type things, but I can't say for sure at this point. Right now, I'm leaning toward humans made it. They just don't want you to know that they're just,
It's so advanced that like.
I think it's advanced. Yeah. Yes.
Do you think that like the probes would fight each other, like have weapons?
It's like Star Wars on Apex Legends.
It's like the
versus
droid
Star Wars.
wars on the moon.
If what now?
Like the probes like fight each other, like the China probe and the United States probe.
All
Oh,
just
probes.
like
Well, we have some probes. Some of our probes simply
Mars, bro.
go around the planet. Some probes actually land on the planet and they start moving around. So right now we don't have battle bots. We don't have China's
I
channel.
watched BattleBot.
Have you ever seen Battle
All
Bots?
right, I'm gonna stop. All right, here we go. Now, let's go. So now you say you know the Fahrenheit scale, and now let's go to Celsius. How much do you know about the Celsius scale?
A lot.
Okay, how much you know?
It's
How about the freezing point of water? I gotta hurry a little bit here, okay?
oh,
0.
All right. Now, if you think about this, and the boiling point of water is 100, this one became very popular because, and the person's name was Celsius. The whole idea of the metric system was to make it so simple that you would want to replace yours. And so numbers like 0 and 100, which is a power of 10, I see it. I understand it. It's simple. It's real simple. Now, most people, you don't, but everybody in the world knows what their body temperature is in Celsius, and you don't. Everybody else in the world knows. I asked Sally Wang today. She knew. Again, anybody who's from another country, they know what their body temperature is in Celsius, and you don't. So we're going to figure that out in just a minute. And also a room temperature. What's a comfortable room temperature if you went to Europe and they said the high was going to be such and such? Would you say it's going to be a nice day?
like 50.
So I'm going to show you how to do that. Now, one thing about the Fahrenheit scale, we're the only people that actually use it. The rest of the world fell in love with Celsius just like they did the metric system. And so you really do have to know both of these. You need to know both. So what I'm going to do here is I'm going to show you a way to memorize. Here's what the book has. The book has something like this in there. How do you actually convert Fahrenheit into Celsius? All right? Everybody ready?
Ready.
So what I'm going to do is, I started this, I don't even know how long ago. It could have been 40 years ago. But I actually made a really, really small rap song before anybody even said there were rap music. And so what I'll do is I have a really small song, And this little song is going to help you memorize how to convert from Fahrenheit to Celsius. So I do. But what I'm going to do, since I've done this so many times, I told people in the other class, I said I really couldn't be a popular singer, because if you had a popular song, everywhere you went, they'd want you to sing the same song, wouldn't they? And after you sing it about 300 times, you know, it's just not your favorite song anymore. So I've done this a few hundred times, but that's okay. So I can get motivated if you give me, I just need a beat like that, kind of like a, oh, I'm getting there. I'm getting there. Oh yeah. The first thing you do, subtract 32 5 nights. Yeah. Okay, that's it. It's a short song. That's how short it is. Wait a minute. Yes, okay. All right. Anyway, so what's happened is a long time ago, when I was first starting to teach, and that was a long time ago, even back then they wanted the kids to learn how to go from Fahrenheit to Celsius. And so I would get this little piece of paper out, because I had to remember this because I was the science teacher, okay? So I had to be smarter than the students. But I had a little piece of paper in there, and I would write that down, and then I'd write this one down, and then I'd put it up, because we didn't do anything. We didn't do anything with it maybe the rest of the year. And then what happened the next year, I'd have to go find that piece of paper again. And by the time, about the second time this happened, I thought, wait a minute, I'm a science teacher. I probably should go ahead and memorize these. I should probably memorize how to do this. So that's when I came up with a dumb song. So the first thing you do, subtract 32 5 ninths. Yeah. So what we're going to do is, we'll try one of these. Let's put this in your calculator. What is body temperature for everybody else in the world except for you? So it's 98.6. First thing you do.
Subtract 32.
Subtract 32.
Now, by the way, does your math teacher taught you about order of operations?
Yeah, you gotta put it in.
PEMDAS.
Okay, so here's what you do. You say subtract 32, say enter, then times 5 ninths, okay?
Wait, can you repeat what we're putting on our calculator?
Just leave your paper.
I got an answer.
Well, the first thing to do is subtract 32, 5 ninths. So 98.6 minus 32, enter, and then say 5 ninths, enter. All right, so what is body temperature for everybody else in the world?
37.
Okay,
Celsius.
all right. There you go. Now, what about a comfortable room? What's a comfortable room temperature in anywhere else except the United States? Let's try that one. 72. What's 72?
I got 3.7.
Okay, now do it again. Do 98.6 minus 32. Now, be careful, because if you don't press enter and you didn't use parentheses, press enter, then say times 5 divided by 9.
Times 5.
Divided by 9. You
I
get,
still got 3.7.
okay, try it again. Put 98.6 minus 32. Enter.
Yeah.
Now, times 5 divided by 9. Enter.
Times 5 divided by 9.
Enter.
3.7.
Does it say what?
E1.
Oh, E1. Oh, okay, that means you have put your calculator in scientific notation mode.
Oh.
Now, E means times 10 to the. So what's 3.7 times 10 to the first?
37.
That's it. So go up to where it says mode. The other one says mode. Press mode. Now, do you see, right now, I bet the box SCI is highlighted. Use your arrow key and go back to normal. And then press enter. All right, here we go. We got to get going here. What's room temperature then?
37.
22, repeating 2.
Okay, about 22. So about 22 degrees is a nice room temperature everywhere else in the world except for here, right? Now, one thing I want to tell you about these scales. Hey, you guys, wait a minute. Okay, up here, okay? Pay attention up here. Even though every science lab probably uses this, almost every science lab and hospitals use it, and the military might use it, and all the world uses it. That's nice. But there's something wrong with both of these scales. Both these scales, something wrong. And what's wrong with it is they have positive and negative numbers. You say, well, so what? What's wrong with that? It's only because you're used to it. If it's minus 10 degrees Fahrenheit, that's pretty cold, isn't it? But let me ask you a question. Let me tell you what's wrong with a scale that has positive and negative. Ready? What is, I'll do it this way. This is Fahrenheit. Well, let's do Celsius. What's twice as hot as 10 degrees Celsius? Okay, that's not true, but I'll tell you, let's do another one, right? What's twice as hot as 0 degrees Celsius?
20 degrees.
See, that's not true either. It's not 0. What's twice as hot as minus 10?
Positive.
You want to say minus 20 because that math thing's kicking in, isn't it? But you know it makes no sense. How can minus 20 be twice as hot as minus 10? I just proved my point. A scale that has positive and negative numbers is bad for mathematics. So if we do mathematical calculations in science, we cannot use the Fahrenheit or the Celsius scale. So what has to happen is we have to change it to a scale that has no negative numbers.
Kelvin.
All right, so what they did is they liked the idea of the Celsius scale, and they found out theoretically the coldest that you could ever have anything is about minus 273 degrees Celsius. Okay, this is absolute 0. Now, this is a nice scale. They like the idea of the scale. They like the idea of 100 degrees between freezing water and boiling. They like that idea. So they didn't want to throw away the Celsius, but they said, let's get rid of the negative numbers. All they had to do then is make this 0. I hereby declare that negative 273 Celsius is also known as 0 kelvins. And so the formula says Celsius plus 273 equals Kelvin. And that's how it worked, right? And if you look right here, see? On this scale here, 0, absolute 0 is okay. Yeah. Okay, so 0 degrees, absolute 0 on this scale is okay.
I get it.
Thank you. Well, anyway, so now what is an ice cube in the Kelvin scale?
273.
Well, it was 0 here. You just add 273, and what do you get? 273. And what is boiling water in the Kelvin scale?
373.1.
See, it makes, so it really is the Celsius scale with no negative numbers. See that? That's pretty neat. Now, I didn't tell you about this one, and I'll show you how I did it. When I was a young teacher, like I said, and I did that stupid little song, first thing you do, subtract 3259. Yeah. I also knew I didn't have to memorize the second one, because the second one was absolutely the opposite. So watch what I'm going to do here. Ready? I'm going to cover this up and show you how to do the second one. How do you change Celsius back into Fahrenheit? Well, you don't add or subtract first, you multiply. That's opposite. You don't use 5/9, you use what? That's opposite. And you don't end up subtracting 32, but you do what? Oh, look at that. And that's how you memorize both of them at the same time. Well, anyway, let's test them out. That's what I would do, test them out. What is boiling water in Celsius? 100. Let's put it in here. What's 100 times 9/5? What's 100 times 9/5?
180.
Add 32?
112.
And that works, doesn't it? Boiling water is 212 Fahrenheit, isn't it? Let's try another one. Let's do 37 degrees Celsius times 9/5 plus 32. Ooh, it works. It works, doesn't it? Now, so if you thought if you weren't sure that you memorized these the right way, you have some little markers you can use to test it out. All right. Well, anyway, this is theoretically the coldest temperature. Now, if you become a top-level physics person, you might hear about some experiments that are, quote, below absolute 0. I'm not going to get into that in this class. But anyway, that's kind of neat. All right, I'm going to show you a little story here, and then we'll be done with this part. Now, I happen to own a company. It's at the top of a mountain. It's called the Acme Water Boiling Company.
You own it?
And no, I've really made up a story. But anyway, I'm going to pretend that I own this company. But we make money. We make money by boiling water, and that's why it's the Acme Water Boiling Company. And now we're on a top of a pretty high mountain, and it's so high that down at the bottom of the mountain, it's like there's even a frozen pond. And by the way, this is an analogy. Okay, so
what should you own it?
anyway, this is an analogy.
Oh, and now.
Well, anyway, my employees that live on this side of the mountain range, they always complain to me because they have to walk all the way up here, and it rains and they kind of slip their way up there, and I didn't want to have to pay for it, but I guess I'm gonna put steps in. So on this side of the mountain, the only company who makes steps is the Fahrenheit Step Company. I said, well, how does this all work? How do you charge me for it? Well, all of our steps are numbered. So we know which one we start with, we know what we end with, and that's how many steps we charge you for. And by the way, can you come out on Monday? Yeah, but you'll be the second job. We have a small job to go, and then we'll come back to your place. Okay. When I got there, they started with step 32. It's an analogy. And then when they got done, they ended up at step 212. Huh. So how many steps did they charge me for?
12 minus 32.
200.
Well, you have a calculator.
Wait, oh yeah, that makes it easier.
168.
All right.
Wow.
So 212, and they started with step 32, didn't they?
180.
All right, everybody get that? Now, watch now. Watch, you're going to miss the best part of the analogy. The only people on the other side of the mountain range that made steps were the Celsius Step Company, and they made their steps differently. But I was the first job for them. So they came out, and their the first step was step 0. And when they got done, they were step 100. So how many steps they charged me for? Now, how did they go the same mountaintop with only 100 steps?
Bigger.
It must have been bigger. Now, let me tell you something, okay? I understand that the honor students, that's you guys, when I ask you to look at numbers like 100 and 180, unfortunately, here's what you do. 180 minus 8, it's 80. This is 80 bigger than that. Okay, so a third grader can tell me that. Then you say, oh, they're both even. A third grader can tell me that too. But what an advanced student would do is always look at numbers in terms of ratios. So what I'm going to do here, I'm going to make a ratio, 100 over 180, and 180 over 100. Now, let's see if that enlightens us at all. So what do you get here? What if we just reduce it? What do you get?
599.
Oh, wait a minute.
Wait a minute.
Ah,
But it's an analogy.
now, it is an analogy. And if you wondered where these numbers came from, why did they use a fraction of 5/9 and 9/5? Now you know. So a Celsius step is 9/5 higher. That's 1.8. Isn't that right? Your book actually doesn't even say 9/5. They said 1.8. But I'm going to try to tell you where those numbers came from. So a Celsius step is 1.8 times bigger than a Fahrenheit scale step. All right, so let's go over here and answer some questions, and I think we'll be done with the temperature scale, and we would have been done with those 7.5 pages in your book. All right, ready? The Kelvin scale is the SI unit of temperature. Why didn't they pick Celsius? Even though everybody uses Celsius, you can't put a scale with positive and negative numbers into mathematical equations. So you have to convert to Kelvin. Oh, by the way, I didn't tell you this. They're called degrees Fahrenheit. They're called degrees Celsius. They are not called degrees Kelvin. They're called kelvins. Okay, they're kelvins.
What's SI?
Now, by the way, I want to tell you something. Let me tell you something here. When I asked you the other day, or not too long ago, what's twice as hot as 0 Celsius? And your math brain said what?
0.
0. You know that doesn't make any sense. And what's twice as hot as minus 10? Your math brain said minus 20. You know that doesn't make any sense. But take a look here. What's twice as hot as 10 kelvins?
100.
Wait. What's twice as hot as 10 kelvins?
20.
20 kelvins. It works.
Oh my God.
What's twice as hot as 200 Kelvin?
400.
It works. All right, let's go on down. Ready? The Kelvin scale is also known as the absolute scale because 0 is absolute 0. Hey, give me, wait. Give me a minute. Wait a minute. One more minute. The Kelvin scale units are the same size as the Celsius. It's just they don't have any negative numbers. There are no negative numbers, no negative temperatures on the Kelvin scale. All chemistry and physics equations that require temperatures have to be in Kelvin. The Fahrenheit scale is named for Fahrenheit, and the Celsius scale is named for
Celsius.
Celsius, and the Kelvin scale is named for
Mr. Calvin.
John Thomson. Now, John Thomson, later, he actually was given a title by the king, and he was actually the baron over this land called Kelvin, so he was called Lord
What's his
Kelvin.
name? John what?
Thomson, but he later he was called Lord Kelvin. He was the lord of the Kelvin area, so that's why we call it the Kelvin scale. Next, there's only look at this one. There's only one temperature where Fahrenheit and Celsius read the same number. I'm not going to tell you that, but when you come back next week, let's see if anybody gets that. If you want to,
Extra credit.
if you like math, if you can do the mathematics of it and show me the equations, I'll give you extra credit. If you just punch around with your calculator, I won't give you any credit. But all right. Well, anyway, I think that's about it. Hey, enjoy your 4 days break. I'm going to be here tomorrow. We have a work day, so we have to go have meetings.